Well, so yes, I'm the founder and CEO of Pi Squared. Um, I am also a professor of computer science at University of Illinois Urbana-Champaign. And some of you may have heard of another company that I founded called Runtime Verification, which is in the business of formal verification and security auditing. Waiting for Diego to ring his bell. And how many people here heard of Pi Squared before coming here? All right, great. Okay, some people heard. How many people here heard of runtime verification? All right, cool. Right, so runtime verification, let me tell you a few words about runtime verification before, the ring stops. So runtime verification uses mathematical definitions, mathematically grounded definitions of programming languages in order to reason about programs. Okay, we call that formal verification. And the bottom line is that if you do not have a mathematically grounded definition of a programming language, then you cannot even talk about correctness, right? How many people know that? Because many people talk about correctness, but very few really understand that you need a mathematical definition before you can talk about correctness. Otherwise, it's just hand waving. Okay. All right. So I'm going to start. Pi Squared is a new company that builds on the same main idea that we need a formal semantics, a formal mathematical definition of a programming language in order to talk about correctness. However, unlike in security auditing companies where we use formal semantics to reason about programs, in Pi Squared, we use formal semantics to guarantee correctness by construction. You don't need to prove anything because things are going to be correct by the way they are constructed. So what we aim at Pi Squared is universality with respect to programming languages. Essentially, we firmly believe, after more than 30 years of work in this field, that the programming language should be a plug-and-play capability in a system. The programming language should allow us to move from one state to another, and we should be able to bring as many programming languages as we want into any ecosystem. Also, we aim at settling with Pi Squared anything that is provably true, anything that you can bring a proof for that is true, that can be settled, right, once and for all. And we also have a novel consensus protocol that I'm not going to talk about here. I'm going to mainly focus on the programming language aspect and how we can connect that with restaking. Our ultimate goal in Pi Squared is basically to bring all programming languages to Web3, right? So we like Web3 developers to write programs in Python, in Java, and even in C, right? So every language should allow us to program in Web3 as well. Pi Squared is a new company. We just started a few months ago, but we build the entire company on 3 novel and orthogonal innovations. The first one is what we call the universal language machine, which allows us, as the name says, to operate with all programming languages. Basically, it allows us to write smart contracts in any programming language for which you have a formal semantics. We already have several of them, and we keep adding more. USL, Universal Settlement Layer, is what allows us to settle truths. So everything that is true, everything that has a proof, either a mathematical proof or a zero knowledge proof, can be settled once and for all and can be used interoperably in any of these programming languages that we can support. And finally, universal consensus is a new idea in consensus, which is based on the belief that we do not need total ordering of transactions in order to to have safety. So we can focus instead on safety. Each application has its own safety guarantees, and as far as those are preserved, then we can have an operating correct protocol. I'm not going to talk about universal consensus here. That will be the topic of another talk, but I'm going to focus on the universal language machine. So what is the problem with universality when we talk about languages, many languages? The problem with languages is that a language is never just a language. It's an ecosystem of tools. We need interpreters, compilers, symbolic execution engines, formal verifiers, and so on and so forth, editors for each programming language. And it is very hard to develop all those in a consistent way and then to bring all them to a new ecosystem of developers. So that is a real barrier. This is my field of research, programming languages. That's what I've done for 30 years. And we know how difficult it is to bring a new language because it's not only just the language; it's always all the system of tools that that come with the language, and that's a real barrier. For that reason, the programming language community has developed what we call language frameworks, which are based on formal semantics of programming languages. So formal semantics, I said it again at the beginning, I say it again, a formal semantics is actually a rigorous mathematical definition of a programming language, a mathematical theory, if you want. Same like geometry or Euclidean geometry is a mathematical theory that allows us to reason about geometric shapes. The same way, we can have a mathematical theory of Python that allows us to reason about Python programs. And what a framework does, and K is one of the frameworks that that we invented about 20 years ago. So what a framework allows you to do is to plug and play a programming language once you have a formal semantics for it. Okay, so you invent your own language called my language. So now once you have the formal semantics of my language, you can plug it, and the framework gives you all the tools that you need for your language: interpreters, compilers, symbolic execution engines, and so on and so forth. And importantly, and this is very important and very hard to understand unless you are trained in this field, is that they are correct by construction. Correct by construction means that you do not have to formally verify them because they are generated from the actual mathematical definition in a way that guarantees correctness. Okay? And pi squared comes from proof of proof, specifically zero knowledge proof of mathematical proof. So the idea of a language framework, as I said, is that gives you everything correct by construction. What that means specifically is that every single thing you do with a programming language, say executing a program, in the end generates under the hood a mathematical proof that you can check step by step. Okay, so that is the mathematical proof of the pi squared. Now, the next step is to check the integrity of the mathematical proof using a zero knowledge circuit. And once you do that, now you have a zero knowledge proof that a mathematical proof has been presented and checked. So the claim is true. Okay, so proof of proof. So this you have a very succinct argument why the claim is correct. And the claim can be in particular a computational claim. This picture is a bit crowded, but you should go scan it from left to right. So to the left, you have a programming language and a program. And to the right, you have a zero knowledge proof, which is also the pipeline that you see in general in verifiable computing. Right, where you have a circuit for a programming language. Now you take a program, execute it, generate a zero knowledge proof. What is different in our approach, in our workflow in pi squared, is that this flow is completely agnostic to the programming language. Okay, the programming language is an input. So you take the programming language and a program, the tool that the framework provides executes the program and generates a mathematical proof, which is right here in the middle. This big pi is the mathematical proof that is being generated by executing the program. And then you check the integrity of the mathematical proof, the second half of the picture, using a mathematical proof checker, but implemented as a zero knowledge circuit. Okay, so this separation of concerns is very important because it allows us to eliminate the implementation of the programming language, the interpreter, or the virtual machine, or the compiler from the trust base. You do not have to trust the interpreter anymore. I do not have to trust the EVM implementation anymore, because the EVM implementation will give you a mathematical proof that tells me that yes, that execution was correct. And now from that mathematical proof, I will extract a zero knowledge proof. So I know that the execution was correct independently of how the EVM is implemented. Okay, so right. So basically, going through mathematical proofs, we eliminate the compilers and interpreters implementations from the trust base, and then we can check the integrity of, or the zero knowledge circuit can be implemented now in any zero knowledge technology that exists, right? So we can use, actually, as a matter of fact, we implemented our proof checker in several of the existing ZK VMs to obtain zero knowledge proofs. And what this allows us effectively to do is to connect any programming language with any ZK technology, okay? As opposed to developing a ZK technology for one particular language, right? Like RISC-0, for example, gives you zero knowledge proofs for RISC-V, okay? Starkware gives you zero knowledge proofs for Cairo, okay? So we completely disconnected the two. Now you can have zero knowledge proofs for any programming language because we go through mathematical proofs. We firmly believe that this is the foundation of a new approach to verifiable computing, which we call verifiable computing 2.0, which has two important properties. First, it is completely universal with respect to the programming languages. And second, is correct by construction. You don't have to prove your circuit for RISC-V correct anymore. Okay? Of course, the elephant in the room is performance. How about performance? Whenever I talked about mathematical proofs and semantics, the first thing that comes to people's mind is, and sometimes they express it very directly, is, well, but this is going to be dead slow. There is no hope that you can go through mathematical proofs and keep up with the performance that we need. And before I even dive into details, the TLDR is that not anymore. That used to be the past. Now, you can execute programs very efficiently using mathematically grounded engines. And let's take a look at this slide that talks about this first component, right? So there are three sources of concern here. First is, can we get an interpreter from a mathematical definition of the language that is fast enough? Forget mathematical proofs, just an interpreter that I extract from the mathematical definition. Is that going to be fast enough? That's the first question. And I'm going to show you numbers for each of these. But the second question is, okay, but then if you generate the mathematical proof, is it going to still be fast enough? Yes, you can generate the interpreter, but the mathematical proof also takes time to generate. And then finally, the ZK proof, can that be fast enough? Well, so in this table, what we did, actually we did lots of experiments, right? We ran programs in different programming languages using native interpreters and then going through mathematical semantics and the interpreter generated from the mathematical semantics. This is just one example, but it's pretty representative. So the first line here takes the program that does 1,000 swaps in Uniswap, compiled with the Solidity compiler, and then executed with Geth. And it takes 248 milliseconds. That's the baseline. Okay. Now, what if we run the same program, but now with the interpreter that we generate from the semantics of Solidity, okay, with the framework? Well, it takes 259 milliseconds, so it's only 5% slower. Okay, so you execute the same program with an actual logic reasoning engine, and you get only 5% degradation in performance. Okay, but we don't stop here. One nice thing with mathematics is that you can get mathematical proofs for the same facts, which are more elegant and more succinct. Okay, we call this proof engineering. So there are ways to do proof engineering. So the mathematical proof that you generate internally in the engine is actually smaller. You know it from school, right? That for the same result, you can have a long and ugly mathematical proof, or you can have a succinct and nice and beautiful proof, right? Which was nicer, it's easier to check, the beautiful and compact one. Same here. So with these mathematical optimizations that are completely automatic under the hood, which cannot be applied, by the way, in interpreters, because you have to go into the world of mathematics to do these optimizations, the performance goes actually to 152 milliseconds. So it's actually faster than running off-the-shelf interpreters. Okay, and I want to emphasize this because it's super important. This is the first time that this really happened, right? Where you can run a program with the formal semantics of the programming language faster than with a manually written ad hoc interpreter. Okay, so whoever tells you that formal semantics is slow, mathematics is slow, tell them, no, not anymore. Okay, now you can run programs really fast using mathematical definitions of languages. Second, what if we want to actually extract from the program execution the mathematical proof object, right, as a standalone object? Well, it's a long story. We'll publish all these results, but the bottom line is that you have to add an order of magnitude, unfortunately, with the current implementations, which is only a few months old, right? We are improving it as we speak. So we hope to get this down to 2 or 3 times, right? So with 2 or 3 times only degradation in performance, basically from a few milliseconds to 3 more milliseconds, you will get an actual mathematical proof that attests for the correctness of the computation in a completely independent way from the implementation of the programming language. You don't have to trust the implementation, you have the mathematical proof that you check. Right? And the final step is to ZK that mathematical proof, the pi squared, the proof of proof. You get a ZK proof of the mathematical proof. And the question is how efficient that is, and that's still work in progress. What we have here are a few numbers using off-the-shelf ZK VMs, like RIS0, Jolt, SP1, Cairo. We implemented the proof checker in all of these because the proof checker is an embarrassingly simple program. It's a very small program, only a few hundred lines of code that we had to implement in these different proof checkers, zero knowledge VMs. And these numbers are preliminary. And if there is one lesson to learn here is that it's not very easy to set up these ZK VMs. Anybody here try to play with ZK VMs? Oh, not too many. All right, okay, some of you. So they are not very easy to set up. RIS0 was very easy to set up, but others were not that easy. But fortunately, the community, the ZK community, is very friendly. So they give you help whenever you need help. So we are going to, so all these are actually public already numbers, and we are going to publish them soon. But essentially, by implementing again the proof checker using a ZK VM, now you can get a universal verifiable computing framework. Okay, you can use any of the ZK VM backends to generate proofs for any programs in any programming languages without compiling, okay, to an intermediate language. All right, so as I said, we are a new company, started only a few months ago, and that's our main idea, how to deploy it, how to implement it. And we believe that actually restaking is a great way to implement it because we have all these proofs, they can be verified. So verify, we don't have to trust. We can this way secure the entire approach by ETH. And the narrative here would be that through pi squared and restaking, we can bring all programming languages to Ethereum. Okay, the programming language is not the barrier anymore. You can plug and play your language. All right, so thank you. If you want to see a demo of this, I welcome you on Thursday. We are going to demonstrate the universal language machine. We'll show you how you can plug and play a language. We'll plug and play together a language in the workshop room. So thank you.